Hi doctor, my name is Jim Ping. Today I'm going to present about the group project of finite element method SEMM3033. The title of our project is Working Frame. I'm from group 3. My group members include Muhammad Aiman bin Jafar and Amirul Hakimi bin Amran. Let me introduce about the working frame. Working frame is also known as the walker. In general, a walker or working frame is a tool for disabled or weak people. They use the walker as an additional support to maintain their balance or stability while walking. When using the walker, there exists the potential that the working frame might break or loosen. Therefore, walker is analyzed in different critical application or load cases to determine the deflection that are going to occur. It is analyzed in terms of maximum loads and the friction between the working frame and the surface to prevent the failure of the walker. The finite element analysis is needed to carry out in order to design the working frame. Performing the finite element analysis allows us to determine the maximum load and pressure, thus can produce a better design and prevent the failure of the worker. Next, I'm going to talk about the problem statement of the project. The material used to manufacture the walker is aluminum alloy 7075T6. The working frame is subjected to different kinds of loads at different locations in the frame. For example, there are loads at the handle, joints, and the leg of the working frame. Hence, finite element method is used for the simulation for loads and stress in the working frame, so that the maximum load and physical behavior of the working frame can be determined. It is very important to do finite element analysis to prevent the working frame from damaging and injuring the user. The objective of this case study is to carry out finite element analysis on the worker. Other than that, another objective is to examine the different load case on the working frame and to determine the most critical situation. Let me talk about the first load case. For both load cases, the weight of the user is assumed to be 70 kg and the weight of the worker is 2.3 kg. First load case is the load applied when user stands up using a walker. This load case is chosen because it is one of the most critical applications for worker. The type of the load for this load case is the weight of the user and the torsion on the handle of the working frame. We will show it by using one side of walker since it is symmetrical to each other. The force on one side of handle is 343.35 Newton and the torsion is 156 Newton meter. The mean impact experienced by the working frame is at the handle. So, the boundary condition are the legs and the frame joined to the handles. Mesh convergence study is done for this load case. The maximum displacement and the stress are simulated from the analysis. The table shows the value for simulation and theoretical. The percentage error for the simulation and theory is calculated to be 10.11% for displacement and 7.70% for stress. From the calculation for percentage error, it is acceptable as the percentage error is around 10%. Next, the three figures here show the enlarged part of von Mises distribution plot. The color intensity indicates the amount of stress in the walker. From the finite element model, it can be shown that most of the region is dark blue, which is 0.6696 kilopascal. The maximum stress happens at the red color region, which is at the joint between the handle and the frame, as shown in the figure. From the stress distribution meter, the maximum von Mises stress is 51.82 megapascal. It is the most critical part as maximum force is exerted on it. The maximum stress is 51.82 megapascal, which is lower than the yield strength, which is 505 megapascal. Therefore, the working frame will not fail.
Hello and good morning, Dr. William. I hope you're in a good health in this MCO period. My name is Muhammad Aiman bin Jafar and I will continue OGP presentation just now. As you can see, I will explain about the displacement distribution plot for case 1, that is stand up. Okay, the two pictures above is the before and after deformation for one side of the working frame. As you can see, we put 3 fixture points for our model, 2 on the both leg and 1 on the joint between the front handle and the working frame. Okay. When the force exerted on the working frame, the front side of the working frame, as you can see in the picture in the blue color, will experience less deformation because of fixture point, while the other side will experience more deformation. This case occurs in the high quality mesh as well as low quality mesh. As you can see, the blue color is the minimum displacement distribution, while the red color is the maximum displacement distribution. For the high quality displacement distribution, the maximum displacement is 0.06694 mm in the red color, while in the dark blue region, the lowest displacement is 0.001 mm. Next, for the draft quality mesh, the maximum displacement is 0.06553 mm, and the dark blue region, the minimum displacement is 0.001 mm. Next, I will explain to you about the factor of safety distribution plot. As you can see in the first picture, all part and the component of the working frame is in the red color. So, we make some adjustment and limit the maximum distribution safety factor around 2000 and get the second picture. As you can see, the critical part is in the red color, that is between the handle and the back side of the working frame. If unwanted thing happen when the person stand up, the most likely place to fail first is the red color. For high quality mesh, the safety factor value gained from the calculation should be 10. The calculated safety factor is similar to the minimum safety factor shown in the simulation distribution plot for high quality mesh. While for the draft quality mesh, the safety factor that is calculated is to be 14.3. The simulation safety factor for draft quality is 15, which is close to the calculated value. The safety factor is considered very high and the working frame is less likely to fail. With this material, the working frame is able to withstand the high stress. Now, I will explain about the second load case, which is friction between floor and worker. This load case occurs when the user is working using this working frame. It is critical to have friction between the floor and the worker to keep the user from falling down. When the user walks with the worker, the friction between the floor and the worker is one of the most critical parts where the load are applied. During this process, the user weight is applied to the working frame handle. The weight of the worker and the user is then applied to the floor, resulting in the friction. This could be put a lot of stress on the working frame. The working frame may break if the stress is too great. Furthermore, it is assumed that the user walks with the worker without the assistance of another person or other external forces. As a result, the user is working solely with the worker. As you can see in the picture, we decide to put only one fixture point, that is between the connector of the front handle and the working frame. And for the forces, on the side handle, we decide to only put the one downward force, that is the weight of the user. And on the leg, as you can see, on the front and the back side on the leg, we can see there are two forces. One forces is the friction force and the downward forces is the weight of the user plus the working frame weight. As you can see, by using simulation, we get the maximum displacement is 1.556 mm and the maximum stress is 34.18 megapascal. But when we use theoretical method, the maximum displacement is 1.512 mm and the maximum stress is 31.1027 megapascal. Pascal. So the percentage error for the maximum displacement is 2.91% and the maximum stress is 9%.
This is the one-meter stress distribution plot for the draft quality mesh and the height quality mesh. Both of them will have a same distribution plot. From the finite element method analysis, we found out that the distribution plot is not uniform due to the irregular shapes of the worker frames. And from the analysis also, we found out that the most critical points that occur for the worker frames is at the holes for each legs of the worker frames, as you can see here. So the brighter color indicates that the one-meter stress is greater compared to darker color. So this is due to the stress concentrations exist at this hole. So the calculations of the stress will be different and it influences the stress. So that's why it has greater stress at the holes compared to other parts of the worker frames. So we move to the displacement distribution plots. So this is the displacement distribution plot. It seems like the one-meter stress distribution plot. The brighter color indicate that the displacement is greater compared to the darker color. So the greater displacement occur at the tips of the legs of the worker frame due to it experience a friction force. This is because the friction force will always oppose the movements of the worker frames. So that's why it has a greater displacement compared to the other parts of the worker frame. So you can see from the analysis, the color is slowly changing from the brighter to the color from the tips of the leg to the top of the worker frames. So this is accurate as the greater stress occur at the tips of the legs of the worker frame. And this is the factor of safety distribution plot for the worker frame. So from the finite element method analysis software, we found out that the height quality match, when we use the height quality match type of match, the factor of safety is 14.77, while when we use the draft quality type of match, the factor of safety is 18. The difference in color is due to the size of the mesh that is being used. So for the high quality mesh, the size is much smaller compared to draft quality mesh. So that's why it gives a accurate and precise reading. So for the conclusion, we can state that the working frame can resist both cases load 1 and load 2 because of the factor safety is greater than 1, but due to the different readings of the factor of safety, we can conclude that the case 1 is more risky compared to the case 2. Because of the factor of safety of the case 1 is much lower compared to the factor of safety of the case 2. However, we can do some modifications to improve the performance of the working frames. We can change the materials of the working frames to materials that have a higher yield strength, such as cast iron, aluminium, and other aluminium alloy or titanium. So this is because when we modify the materials, so the computations of the factor of safety, the diffractions, and the one misses will be the same. That's all.